Good afternoon, everyone. Welcome. I'm Chris Doherty, Vice President for Academic Affairs and Dean of the Faculty here at Chestnut Hill College. It's my privilege to call us to assembly for the 29th Annual Biomedical Lecture by Dr. Drew Weissman and his address, Action Plan, What to Do After 10 Billion Doses of Vaccine. Thanks especially to Dr. Lakshmi Atchison for her leadership and stewardship of the Biomedical Lecture Series. Today, we, together once again, become part of the college's tradition of welcoming leaders in the biomedical sciences as they share their expertise, their innovations, and their stories. This lecture series is one of the college's proudest and deepest traditions, rooted in the excellence in teaching and learning that is a hallmark of the Chestnut Hill experience. I have the additional pleasure and privilege this afternoon to introduce, for the first time at the Biomedical Lecture, Dr. William Latimer, Chestnut Hill College's 7th president, as he welcomes us today. Before assuming the presidency this July, Dr. Latimer had established a distinguished career in higher education, rising through the ranks of faculty to administration at institutions including the College of New Rochelle, City University of New York, Lehman College, the University of Florida, Johns Hopkins University, and Mercy College. Holding a PhD in clinical psychology from the University of Rhode Island and an MPH in epidemiology from the University of Minnesota, Dr. Latimer has also experienced immense success in other areas, including fundraising, grant writing initiatives, strategic planning, enrollment management, and forming and sustaining community partnerships across both civic and business sectors. Please join me in welcoming Dr. Latimer to the podium today.
Thank you, Chris. That was very kind. I want to also thank Dr. Atchison for doing such an amazing job bringing such noteworthy researchers to Chestnut Hill College to share their expertise and their science. It's just so important. And I want to thank Dr. Drew Weissman for being here to talk about his work. I just spent about 5 minutes speaking with him. We went through about 7 diseases, 12 vaccines, and 30 years of research. And it really, it brought me back to the 11 years that I spent, as Chris said, at Johns Hopkins University, and my main charge at that institution was research. What I want to say to this group, especially the students, I am thrilled that you're here. I mean, for me, and obviously the faculty too, but for the students, I'm so grateful that Dr. Weissman is here. Listen to what he has to say, and please know each and every one of you can do what he does. You finish your undergraduate degree, go on for your PhD in epidemiology or an MD in medicine, and complement that with research. And then you can spend your life studying the things that you want to study and moving the needle and changing the world and making it a better place. The kinds of things that Dr. Weissman has done is curing disease, preventing disease. The work he's doing is saving literally millions of lives. And that's what science can do. And each of you can do it. And Chestnut Hill College is a part of that journey. And then beyond Chestnut Hill College, you can go to a place like Penn and work with a scientist like Dr. Weissman and change the world. It's an absolute thrill to have him here. With that said, I believe I will be turning it over to Dr. Joe Kulkowski, who's right here, who will be giving some introductory remarks. Dr. Weissman, thank you so much.
Well, that's a first. I get to follow the president of the college. Thank you, Dr. Latimer. Greetings to everybody, Vice President Doherty, Dean Meacham, faculty, staff, guests, and most importantly, students. 2 years ago, around this time, this room lay fallow and empty. And now, as I look over this crowded room, the dynamic is considerably different. I believe we owe a great deal of gratitude to one person among us today for such a remarkable rebound from a horribly devastating pandemic. And that is our invited guest, Dr. Drew Weissman. Without his determined efforts, we might otherwise be in the same circumstance today as we had faced 24 months ago. As always, Lakshmi, it's a pleasure to be part of the magic you have created every semester for the last 29 years, bringing the best and the brightest scientists and clinicians to Chestnut Hill College. This event is no exception. Actually, for me, it's an epitome, as I feel a special kindred with Dr. Weissman's research, what he touched on a little bit earlier. Isn't it almost crazy, unimaginable that Dr. Weissman is here with us today, who is literally above all others responsible for saving countless numbers of lives by shepherding us out of a pandemic with an approach to vaccination that is incredibly imaginative and facile. There's my first slide, thank you. Dr. Weissman, I want to thank you so much for this quote you gave in a recent interview. Your advocacy for basic research is so very welcome and important. Your own basic research clearly served as the platform and the basis for the development of your mRNA-based anti-COVID vaccine. I can't help but be cognizant and be concerned for so many postdocs and young and old primary investigators that are pursuing their research dreams on a razor-thin budget or perhaps none at all. It's actually heartbreaking to me that somehow humankind has the resources to fund instruments of mass destruction, but too often offers only very slim resources for good, just, and noble causes for individuals that pursue scientific research that always will have the potential to treat or cure a multitude of serious medical disorders and diseases, as your own work has profoundly shown us. Next slide, please. I hope you enjoy my tribute to you, Dr. Weissman, in prose as an acknowledgement and expression of gratitude for your accomplishments and my thankfulness and our thankfulness as a community for your presence with us here today. So the title of this is, If Not For You. It's taken from a song from a singer-songwriter that's an old rock and roller, and maybe somebody in the audience might recognize that title, I don't know. But may I have the next slide, please? So it all started with the world thrown askew by a coronavirus, COVID-19, that was seemingly new. Its lethal effect was a major issue, and its infectious spread made it hard to subdue. The origin of COVID-19 remains a controversial issue, the initial speculations of which there were only a few. Perhaps a pangolin, a bat, or even a lab tech too. Unfortunately, this controversy continues with much ballyhoo. Dr. Rand Paul versus Dr. Fauci, but at least Dr. Fauci has a better hairdo. So the pandemic raged on with little to do, info so confusing enough from even the WHO, the World Health Organization. But thankfully, behind the scenes worked a team led by two, they were brilliant scientists, Catalin and Drew. While others were pushing hydroxychloroquine were frankly cuckoo, oddly yet was an injection of disinfectant suggested by you-know-who. So Greg, can you play that short clip? You hit that red arrow.
Thank you very much. So I'm going to ask Bill a question that probably some of you are thinking of if you're totally into that world, which I find to be very interesting. So supposing we hit the body with a tremendous, whether it's ultraviolet or just very powerful light, and I think you said that hasn't been checked, but you're going to test it. And then I said, supposing you brought the light inside the body, which you can do either through the skin or in some other way. And I think you said you're going to test that too. Sounds interesting. Right, and then I see the disinfectant where it knocks it out in a minute, 1 minute. And is there a way we can do something like that by injection inside or almost a cleaning? Because you see it gets on the lungs and it does a tremendous number of the lungs. So it'd be interesting to check that. So that you're going to have to use medical doctors with. But it sounds interesting to me. So we'll see. But the whole concept of the light, the way it kills it in 1 minute, that's pretty powerful.
I'm not making a political statement. That's just a circumstance of the pandemic as it evolved over time. But thankfully, mRNA and lipids were Drew and Catlin's specialty brew, creating a vaccine that arrived right on cue. Next slide. However, one problem emerged before the vaccine's debut. The immune system rejected the mRNA's natural U. The solution to the problem didn't fall from the blue, and it certainly presented an unexpected snafu. Though adding a methyl group to U was a brilliant breakthrough, and perhaps some of the older folk in the audience might get this symbolism. Next slide, please. Oops. So for many, the vaccine is still considered taboo. One reason cited was it was just too brand new. I guess we can all have our own point of view, but I think it's unfortunate. Whether you want the vaccine or not, what's the need for us to argue? Next slide. So the story goes on for this great scientist, Drew. His fame is sealed forever, his kudos overwhelmingly due. Students, his persistence in research is a great example for you. And by the way, UPenn is very happy with their shared revenue too. Next slide. I guess you could play the clip. Let me say this. So Dr. Wiseman, your development of the COVID mRNA-based vaccine surely spared the lives of countless individuals. If not for you, the title of this presentation, so many could not have enjoyed the freshness and the renewed beauty of spring, or the song of robins rejoicing in the joy of being alive. Thank you, Dr. Weissman, for your tireless efforts and your concern for the well-being of mankind. You can play the clip. Thank you. Dr. Wiseman, thank you so very, very much for being here today. And now our dearest Dr. Lakshmi Atchison will formally introduce today's speaker. Thank you all.
Good afternoon, all of you. President Latimer, ladies and gentlemen, thank you, Dr. Latimer, Dr. Daugherty, and Dr. Kulkarski for your kind remarks. I thank you all for coming. If you are a first-timer, we are happy you are with us. If you are a second-timer, we are happy you are back with us. If you are an all-timer, we are happy you are stuck with us. Okay, I am happy to welcome again our new president for Chestnut Hill College, Dr. William Latimer. Seen on this picture on the right side is the chair, board of directors of Chestnut Hill College, Kathy Lockyer Moulton. She was not able to be here today because she's under the weather. Kathy took the major task of leading the search committee along with other board members, staff, faculty, and students who all worked tirelessly in making the best choice in appointing our new president. And it is a pleasure to have you, Dr. Latimer, as our new president of Chestnut Hill College, 7th president of Chestnut Hill College. We wish you continued success in this place. The most valuable person who saved millions of people globally from the deadly pandemic is our keynote speaker today. It's a great honor to welcome our distinguished guest, Dr. Drew Weissman, to Chestnut Hill College. My husband, Michael, who is here, also from University of Pennsylvania, was very helpful in bringing Dr. Weissman here. Michael took my personal invitation and placed it on Dr. Weissman's desk, and he graciously accepted my invitation. So it's a great pleasure and a privilege for me to introduce to you our distinguished speaker today. Many of you may know that Time Magazine 2021 selected Penn scientists Drew Weissman and Caitlin Carico as the Times Hero of the Year for their groundbreaking discovery for helping to develop COVID-19 vaccines using messenger RNA vaccine platform, which you see in the cartoon. This is truly extraordinary. Dr. Weissman's original research published in 2005 on nucleoside modifications and the evolutionary origin of RNA has now become the historic paper of the century. Dr. Weissman, in collaboration with Dr. Carico, discovered the ability of modified nucleosides in RNA to suppress activation of innate immune sensors and increase the translation of messenger RNA containing certain modified nucleosides. It is this nucleoside modified messenger RNA vaccine platform that Weissman's lab created is used in the first 2 FDA-approved COVID-19 vaccines by Pfizer, BioNTech, and Moderna. This vaccine was deployed worldwide in 2020 against the COVID-19 pandemic, which every one of us witnessed. These vaccines show greater than 90% efficacy and outstanding safety in clinical use. This flow diagram is just for our students to understand how vaccine works. A modified nucleoside messenger RNA protein from COVID-19, when injected into our body, our B lymphocytes recognize the foreign protein and makes antibodies. How awesome is that? And we are protected. This powerful tool Dr. Weissman developed 15 years ago was rightly put to use during the pandemic, saving the global population. Dr. Weissman hopes the same technology can be used to develop vaccines against influenza virus and many pathogens like herpes, HIV, coronavirus variants, malaria, tuberculosis, and many others. According to Dr. Weissman, vaccines prevent 4 to 5 million deaths per year, making them the principal tool of medical intervention globally. Dr. Weissman's lab is also developing nucleoside-modified messenger RNA for therapeutic protein delivery. Such messenger RNA LNPs are also developed for gene therapy. His lab is also working on CRISPR-Cas9 knockout to treat transthyretin amyloidosis and has shown success in phase 1 trials. His lab has developed the ability to target specific cells and organs with LNPs, allowing specific delivery of gene editing and insertion systems to treat diseases such as sickle cell anemia. Therefore, nucleoside-modified messenger RNA will have an enormous potential in the development of new medical therapies. Dr. Weissman, Drew Weissman, MD, PhD, is a professor of medicine at the Perelman School of Medicine, University of Pennsylvania. He received his bachelor's and master's degree from Brandeis University, majoring in biochemistry and enzymology. He performed his graduate work in immunology and microbiology and received the MD and PhD from Boston University School of Medicine. Dr. Weissman did his fellowship at the National Institutes of Health under the supervision of Dr. Anthony Fauci, who is the current director of the National Institute of Allergy and Infectious Diseases. Shown in this picture are three great experts in immunology, infectious diseases, and vaccinology. Dr. Paul Offit, many of you may know, was our keynote speaker in 2017. Dr. Weissman is our today's speaker today. It is my dream, it is my sincere hope to have Dr. Anthony Fauci in spring 2023. These great men have saved humanity. Dr. Weissman received numerous recognitions and awards within 1 year. As you can see, from 21 to 22, he received so many awards, including Lasker DeBakey Award, Tang Prize Laureate Award in Biopharmaceutical Science. These two awards are given to the outstanding work in biomedical research and biopharmaceutical research in the understanding, diagnosing, treating, preventing major human diseases to improve human health. Dr. Weissman has done it all. Majority of us in this room are living proof of getting the COVID-19 vaccine based on his award-winning research. Just 2 days ago, Dr. Weissman received another award. He was elected to National Academy of Medicine. Next week, he's getting more awards from Canada. Receiving honors and awards are routine affair for people like Dr. Weissman. How many of us can say that? Dr. Weissman, your work has impacted the global population, saving millions of people during the pandemic. In our Chestnut Hill College Distinguished Lecture Series, you will join the ranks of all our laureates and Nobel laureates who have impacted the global population, thus saving millions of lives. In addition, our Distinguished Speaker Series also includes elite professionals of high caliber, as seen here. All these speakers have graciously accepted my invitation. They have been extremely generous to spend their entire afternoon with us, offer their keynote speaker without an honorarium. This is truly very humbling for me, and I'm truly honored. I owe each one of them my deep gratitude for their presence, including you, Dr. Weissman, and for exalting this Chestnut Hill College Biomedical Lecture Series that is so unique in this nation and putting Chestnut Hill College on global map. According to a report in the Washington Post, Weissman gets fan mail from all over the world, thanking him for his work that made COVID-19 vaccine possible. One said, "You have made hugs and closeness possible again," asking him for a picture or his autograph. Folks, we are so fortunate that he is here. You can take selfie and use this great opportunity, of course, with his permission. Dr. Weissman is an author of hundreds of research papers. I can be standing here all day about his accomplishments. Dr. Weissman is inventor of many patents which detail the modifications required to make RNA suitable for vaccines and medical therapies. I asked Dr. Weissman for a catchy title for today's talk, and he gave me this title, Action Plan: What to Do After 10 Billion Doses of Vaccine. I know we can all get boosters with this number, but the rest I'm going to leave it to the speaker to say what future holds with RNA research. Drew, I am deeply grateful that you are here and you took my invitation amidst your extraordinary busy schedule, and you are here, and I'm truly honored for your presence, and I'm grateful for your coming. Once again, on behalf of our President, Dr. William Latimer, and Vice President, Dr. Christopher Daugherty, I thank you all for coming to Chestnut Hill College. Ladies and gentlemen, it is my distinct honor and a privilege to introduce to you the person of the year, person of the century, who saved millions of people from saved life in global population. Please join me to welcome Dr. Drew Weissman. Joseph Karikoff, would you please come to the podium and honor our speaker with this garland?
So that was an incredibly wonderful introduction. I'm not sure I should speak after that because I'm only going to let you down no matter what I say. When presenting to an audience like this, it's very difficult because there's such a range of knowledge. And no matter what, some people are going to be bored because it's too simple and other people are going to have trouble understanding. So I tried to hit a middle ground, and I'll be around afterwards if people have questions about anything or any unknowns. So I like to start off when talking about students because I'm commonly asked, what is important for a basic science researcher? What do they have? What are the characteristics? And my response is always, there are no characteristics that define somebody who would do well in basic science. The important thing is curiosity. It's the desire to research, to understand, to learn about things. And if you don't have that, then basic science is probably not a good place for you. Basic science research is really like a whack-a-mole game. You've got tens, hundreds, thousands of hypotheses, of questions, of unknowns that are currently popping up in your mind, and you have to pick the ones that are the best. I was in Spain last year and found this picture in a Byzantine church. And if you look at it, the whack-a-mole game actually started back then where the mole was hitting the people. So times have changed a bit. So I always like to start off, and this goes back to conversations I had with leaders in the field, people like Gary Nabel and Tony Fauci and numerous Nobel Prize winners early in the 2000s when I would go to a conference and present my RNA data, and they would say to me, "That's very interesting, Drew, but when are you going to do something useful?" RNA had failed clinical trials. No biotechs or pharmaceuticals had any interest in it. And they thought I was wasting my time studying RNA. And they were trying to convince me to move on to something else. And my argument was always, well, RNA has enormous potential. At this time, and even now, the largest field in pharmaceutical sciences are monoclonal antibodies. There are monoclonal antibody treatments for cancer, autoimmune diseases, hypercholesterolemia, osteoporosis, migraines, and they keep developing more. The problem with monoclonal antibodies is this is what it takes to make them in a factory. You start with a 50,000 liter drum full of cells. Those cells make your protein. Then you have to purify that protein away from all the fetal calf serum and other cell culture components. For every new protein, you start over. The cost of a monoclonal antibody treatment is $50,000 to $100,000 a year. So that's excessive for much of America, and it's completely untouchable for the majority of the world. With RNA, RNA is made in a simple enzymatic reaction. There are no human cells. It's simply an enzyme and some chemicals. For the current vaccines, J&J uses 50,000 liter drums to make their adenovirus vaccine. Moderna and BioNTech use 100 liter bioreactors to run their simple enzymatic reaction. They both produce about the same number of doses of vaccine. For RNA, if you want to change vaccines, you want to put a new variant in, or you want to make a flu vaccine or HIV or anything else, you just pop in a new sequence and everything else is identical. For protein vaccines, for adenovirus vaccine, you start over and you reinvent everything. So RNA is fast, simple, and as we've seen, very easy to expand. I'm the one up here getting the recognition, but I'm certainly not the only person that's responsible. There were thousands and thousands of researchers before I ever started doing any work who were investigating RNA. There are thousands and thousands currently working, making RNA better, different, more interesting for new therapeutics. And most exciting in the future, there's going to be thousands, tens of thousands, who knows how many researchers who have taken what Katie and I have started with and turning this into new disease therapies, new vaccines. The potential is really unbelievable. So when you think about vaccines, the first vaccine that we know of was actually invented in the late 1700s. And this, it's a nice story. Edward Jenner was a physician in England, and this is during the smallpox epidemic at the time. And he noticed that milkmaids were not developing smallpox. And he also noted that the cows that they were milking had similar looking pox lesions. So his idea was to break open those pox lesions and inject the fluid in them into people's arms as a vaccine. Now you have to remember, they didn't know what a virus was or what a bacteria was. They thought that disease transmission was due to bad air, bad water, something, who knows where it came from. But he had the idea that the cows had pox, the milkmaids were protected, let's use that. That was the first vaccine. That vaccine was mandatory for the United States, for anybody in the Revolutionary Army. Since that time, many new vaccines have been developed, and this is just a partial list, and many different platforms. So when we say platforms, it's the broad group. So there are live virus vaccines. These are things like measles, mumps, rubella, and the nasal influenza vaccine. There are inactivated protein vaccines, like the tetanus toxoid vaccine or the hepatitis B vaccine. There are viral vectors. This is best characterized by the adenoviral. Adenovirus is a common cold virus, and they plug in a protein for the disease of interest into it, and it works very well. The DNA and the RNA are the newest vaccine vectors that have been developed. So Katie and I developed nucleoside-modified mRNA in the early 2000s. And Katie was in the Department of Neurosurgery and worked on developing treatments for stroke, for brain inflammation, and I started working on vaccines. The reason for this was some interesting findings. So currently, and at the time, the best vaccines are live virus vaccines. They give the most potent responses and protection. The problem is that the FDA hates live virus vaccines because it doesn't take much for that virus to change and become pathologic and give you the disease instead of curing you from getting the disease. RNA shares a property with viral vectors that it makes protein for a long time, and that leads to better immune responses. So when we first started making vaccines, we had to compare them to something. And this was the current literature. So what these are is scientists do an experiment where they make a new vaccine, they immunize mice, and they test how much neutralization can the mice do. And it's done usually as a fraction, which is the dilution of blood that protects the animal. And what we saw is that typical influenza vaccines gave titers of 1 to 100, which isn't bad. 1 to 40 is protective. But when we made our RNA vaccine, we did the exact same thing they did with all of these other vaccines. But what you can see is that the RNA vaccine gave a titer of 1 to 2,500. So that's 50 times better than the standard influenza vaccine. That's 5 times better than live virus infection. In theory, you're not supposed to do better than live virus infection. When we showed this to pharmaceutical companies and biotech companies, they got very excited because usually new vaccines are twice as good and people get excited. This vaccine was 50 times better and people got very excited by it. But we were immunologists and we wanted to understand how the vaccine works. So this is a cartoon of how B cell responses occur. And what happens is you vaccinate somebody and the vaccine is taken up by a type of B cell called a follicular B cell. That follicular B cell goes and informs what's known as a germinal center B cell. These are the cells that rapidly proliferate, expand, increase the affinity, so make better antibodies, and then produce memory B cells, which are around forever, that protect you from the next time you're exposed to the virus, or what are known as plasma cells that secrete the antibody in the bone marrow, so you've got constant protection. We measured those different populations. And the way we measured them is we added a protein of hemagglutinin, which is what we vaccinated against. So what that does is you measure only the B cells that are making antibody that recognizes hemagglutinin on the virus. And what we found is that with every type of B cell, we had 50-fold more antigen-specific B cells. Again, that's a huge increase, and it shows you the potency of this vaccine. We looked in the bone marrow. So the bone marrow is where our antibodies are made. These are where they're called plasma cells, sit and secrete antibody. And they can do it for weeks, months, or years. And the more antibody they make, the higher your levels of antibody. We left some mice for over a year. Mice live about 2 years, so this is half their lifespan, and measured hemagglutinin-specific antibody in the bone marrow, and the number was enormous. So it told us we had long-lived, high-affinity, effective antibodies. But again, as an immunologist, we wanted to know the mechanism. So this is complicated science, and I'll try and make it understandable. When B cells see an antigen and go on to produce antibodies, they require help. And the immune system is designed to supply help to everything. The help comes from what are called CD4 positive T cells. There are different kinds of helper T cells. Some of them make better killer cells, which are effective for things like cancer. Some of them make macrophages better killers to protect against tuberculosis. And some of them stimulate germinal center B cells. And those are known as T follicular helper cells. So we measured these cells, and we wanted to know, does the RNA vaccine work by inducing better help for the B cell response? We compared it to a protein antigen versus an RNA antigen. And as you can see, there's just no comparison to the stimulation of these specialized helper T cells. So the vaccine works because it induces help to make better B cell responses. My lab has had a long time interest in developing a variety of different vaccines. This is a partial list of the vaccines that we and others are working on. And you'll notice we mainly work on vaccines that previous vaccines have failed. So things like HIV or hepatitis C or herpes simplex that causes herpes disease, norovirus that causes GI outbreaks mainly on cruise ships and isolated and congested regions, C. difficile, malaria, which is one of the leading killers in the world. Previous vaccines have failed in all of these, and the RNA vaccine is showing good success so far, and these are going towards clinical trials to try and make new vaccines. We've also developed vaccines for non-infectious diseases. So we have vaccines for food allergies. Anybody here that has a child with a peanut allergy knows their life is incredibly difficult. Every day they fear that their child will go to school and be exposed to a peanut and end up in the hospital. We figured out how to make a vaccine that prevents peanut allergies. We similarly are making vaccines that prevent aeroallergens. Those are things like dust mites and pollen from trees and grass and flowers. So we hope to have vaccines that easily prevent allergies instead of the weekly allergy shots that some of us have had to take. We're also making vaccines for autoimmune diseases. Currently, most autoimmune diseases are treated with immunosuppressive drugs. And those patients know they have to be careful because their immune systems are suppressed. And if they get COVID, it could be a much more severe disease. We're working on vaccines that don't require immunosuppression, that the vaccine turns off the autoimmune response. We're also working on a variety of cancer vaccines. These are the vaccines that are going into phase 1 clinical trials right now. Some of them are enrolling patients, others will be soon. And it just highlights the list I just showed you. We've also got a bunch of vaccines that are about to enter clinical trials. So RNA is here to stay. There are many vaccines that are being developed, and the hope is that it's a better vaccine platform that will result in vaccines that are protective. Another thing that we have a big interest in is genetic diseases. Sickle cell anemia is probably the characteristic genetic disease. 300,000 people a year are born with sickle cell disease. They're mainly in Africa, but India, the Middle East, the US, and other countries have significant numbers. The problem with sickle cell is it's a debilitating disease. It's a painful disease. It's characterized by pain in many organs and many organ systems. Up until recently, sickle cell patients didn't live much past their mid-20s. Better medicine has improved that, but it's still a miserable disease to live with. The problem is that the gene therapy required cost about $1 million per patient. And it's a very complicated procedure. You can't do that to 300,000 people in Africa, India, and Asia a year. So we're working on ways of fixing that. Something that I've had a long-term interest is equity, is the distribution of vaccines and therapeutics across the world. So this is a colored map of the world population. And the United States, Europe, even China has moderate populations. Most of the people in the world are in Africa and South America and Asia. The problem is, if you look at monetary wealth distribution, most of the money in the world is in the United States, Europe, Australia, but the regions where malaria and other diseases are the highest have the least amount of money in the world. So the question comes, how does that fix itself? The other problem is malaria is mainly in the regions of the world that have the highest populations and the lowest amount of money. And when you're thinking about medical therapeutics, that doesn't work because a lack of money means a lack of development of new drugs. And a lack of a disease where the money is in the North America and Europe means a lack of interest by pharmaceutical companies to develop a treatment that has to go to a part of the world that has little money. So early on in the pandemic, I started working with a group in Thailand to make a Thai vaccine. And they came to me, and I have been working with them for almost 10 years on vaccines in general. But they came to me and said they were worried that any vaccine made in the West by a pharmaceutical company in the West wouldn't be available in Thailand or Southeast Asia for years. And they weren't willing to live with COVID, with the deaths, with the shutdowns. And they asked, could they make their own COVID vaccine? And I of course, said yes. And we developed a Thai version of the mRNA COVID-19 vaccine. These are the phase 1 clinical results. And we're comparing it to the Pfizer vaccine. But what you can see is that the Thai vaccine is actually better than the Pfizer vaccine, which is better than what we see in patients. So Thailand was able to make their own vaccine that turned out to be better than Pfizer's. This is Kiat, my collaborator in Thailand, and the Chula VRC, where the vaccine was developed. But we had another job. We made the vaccine, but we didn't have a place to produce the vaccine. And production of a vaccine requires what's called GMP conditions. And they're highly specialized conditions of negative pressure, of masking, gowning, cleaning, record keeping, that increases the cost of production by 10 to 100-fold. And these buildings cost many millions of dollars to build. But we had the commitment of the Thai government and the Princess of Thailand, and we built a building that could make GMP quality vaccine for distribution in Thailand and all of Southeast Asia. This is the building. And they're now producing vaccine that's being distributed to their residents. I also started working with South Africa, and we built a GMP facility in South Africa. This one was a little bit different. The idea of this center was to be a site where anybody who wanted to make a GMP quality vaccine site in their country, in their regions, could go to South Africa and learn how to build the company, how to set up GMP conditions, how to make RNA LNP vaccines. They've now trained over 100 different groups who are going back and setting up their own GMP facilities all around the world, including Eastern Europe and South America, places where there is an availability of RNA therapeutics. The idea is that if you give a community, a region, a country access to RNA production, and you work with their scientists to develop RNA therapeutics, they'll make the therapeutics that they need. So Pfizer and Moderna have little interest in making malaria vaccines because it's a money-losing operation. But in South Africa and the rest of Africa, Rwanda, malaria is a huge problem. They're now making their own malaria vaccines. In Southeast Asia, dengue and tularemia are big problems. But pharmaceutical companies have no interest because they can't make money. Thailand, Vietnam, Malaysia, Singapore are now working on tularemia and dengue vaccines for their populations. So you're giving access to the technology and for the ability to make the vaccine in their regions, and you're giving local populations controls over what they can produce. And I think that's what gives us equity across the world. So the other thing that my lab is interested in is other things you can do with RNA. And when Katie and I first started, we had a list of everything you could do with RNA. And it went on for pages and pages. It included all of the vaccines, gene therapies, and many other therapeutics. And this just gives you a quick outline of all the different kind of therapeutics you can develop. And I'll talk about a few of them. So we've developed a way of using RNA to treat brain disorders. When somebody has a stroke, this is what the CAT scan of their brain looks like right after the stroke. And what you can see here, this dark area, this is dead brain. So this is supplied by an artery that gets plugged up, and the brain down from that artery dies. But this isn't the big problem with most strokes. If you follow these patients for 3 to 7 days, the stroke expands. So going from this to now almost all of the half of this brain is now dead. And that's because the stroke causes inflammation, which causes edema and pressure on the surrounding brain that then dies. So we're working on ways to prevent the initial stroke, but we also need to work on ways to prevent the edema inflammation so that strokes don't become severe and become less deadly. So to do this, we have a model system. This is a mouse, this is a microinjector. And what we can do is we can inject an inflammatory protein into one side of their brain. So that way they have inflammation on one half and nothing on the other half. We then made an RNA LNP drug that we targeted delivery to the brain. And we do that by adding an antibody that binds a protein that's expressed on the blood-brain barrier. So now when you've got brain inflammation, the lipid nanoparticles are taken up and the RNA makes a protein that's therapeutic. What we're measuring here is edema, is inflammation. It's vascular leakage, which is what leads to the surrounding brain killing. In the absence of treatment, this is the amount of leakage out of the vessels. This is normal. With the delivery of these targeted LNPs with a therapeutic protein that stops edema, we return this back to baseline. So this, in theory, will get rid of any edema, inflammation, and surrounding brain death. We're continuing to develop other brain therapies for things like Parkinson's, ALS, Alzheimer's, and other neurodegenerative disorders. We've extended our targeting technology to 3 main things. Stem cells, so bone marrow stem cells. These are the cells that make every cell that's in your blood and a variety of others. The genetic defects include things like sickle cell anemia, a variety of other anemias, and all of the immune system disorders, the bubble boy, SCID kids, are genetic defects like this. We've targeted T cells, and I'll describe what we do with those, and the endothelial cells I just described, and we'll show you a little more. The way we do this was actually very simple. So this is what a lipid nanoparticle looks like. It has the RNA on the inside. They're covered in the lipids, the fat, and then they have a small amount of polyethylene glycol, which is a protective layer on the outside of the LNP. What we did is we attached antibodies or pieces of antibodies that bound to specific cells. So now when you inject these into an animal, they go to what the antibody is directed against. Importantly, when we did this, we didn't change the lipid nanoparticles. They got a little bit bigger, their charge remained the same, and most importantly, they retain function. So what that means is the job of a lipid nanoparticle is to be taken up by a cell and deliver the RNA to the cell. That's how the vaccine works. The RNA encodes for the coronavirus spike protein. In this case, we used a reporter protein, and you could see in the absence of targeting, these endothelial cells didn't make any protein. So the LNPs weren't delivered and no RNA was translated. When we added a targeting molecule, now we get high levels of translation of the reporter protein. So the LNPs are taken up by the cells and the protein is made. We injected these targeted LNPs into mice, and we can see under normal conditions, most of the activity, so this is a reporter protein, and we're measuring light production from the liver. The RNA encodes what's called a luciferase protein. That's the protein in fireflies that make their tails glow at night. And we take that protein and we can make mice glow. And that's what we're measuring here. When we target it to an endothelial cell, the lungs light up. Lungs have the highest concentration of endothelial cells. So now we're specifically targeting the LNPs to organs they otherwise wouldn't go to. In Tony's lab, I worked on HIV, and I've had a long-term interest in HIV. So we wanted to see, could we target T cells? And one of our main interests was as a form of HIV cure. So HIV treatment has been revolutionized by antiretroviral therapy. But what we know is that you have to take the drugs for the rest of your life. And that's because there are latent proviruses. So what that means is that there is the DNA of a virus in the cells, in the chromosomes of the cells, that are there for a lifetime. And the minute you stop retroviral therapy, the virus comes back. So the idea was, could we, and that provirus is in T cells. The idea is, if we could target T cells and deliver an enzyme that inactivates the provirus, we could cure HIV. So we added an antibody to the surface of the CD4s, and when we did that, we had high levels of binding. Importantly, when we added the antibody, we could get the RNA translated in the T cells. So we could deliver the RNA and make a protein of interest. When we injected the animals, we see the spleen is lighting up. The spleen is a lymphoid organ that has CD4 positive T cells in it. But most importantly, we re-imaged those animals after we removed all of the organs on the previous slide. And what we're seeing here, these are lymph nodes. So all of us have thousands of lymph nodes that drain tissues, and the cells interact there and form immune responses. And what this is telling us is that we could give LNPs intravenously into the circulation. they could escape from the circulation, go into the tissues of the body, into the draining lymphatics to a draining lymph node, and still be taken up by CD4 positive T cells and make the protein from the RNA. So they retained function and could be delivered to any tissue or cell in the body. We switched to a reporter mouse. This is a bit complicated, but the way the mouse is made is it has a protein that is fluorescent. So it shines green or red. And you put a stop codon that blocks its expression. And you add an enzyme that cuts out the stop codon. So it's kind of like Cas9, but acts a little bit differently. So that you know that you've delivered your RNA LNPs when the cells turn green. And we did that with the CD4 targeting T cells. And this is green measurement in this direction. And we see that with targeting to CD4, we get high levels of green cells. So we're targeting T cells. What's most important, though, this is an activation marker. So most T cells are resting. Some 15% or so are activated. We're delivering the RNA to resting T cells. That's also where the HIV resides that we have to cut out. So we're able to actively deliver an enzyme that kills latent HIV in the T cells. This is going into clinical trials as part of an HIV cure. We've developed a number of other targeting therapies. So you probably haven't been exposed to CAR T cells yet. What a CAR T cell is, this is a CD8 positive T cell. They recognize a small peptide from a virus or a cancer cell. And they're not very effective at getting rid of cancer, which is why cancer shows up in otherwise healthy people. But people from St. Jude's had the idea that they could change the T cell receptor and add to it an antibody that bound a tumor marker, so an antigen that's expressed by tumor cells. And they could turn killer T cells to kill any tumor that had that protein on it. The ones that were first FDA approved were for B cells, lymphomas and leukemias. They changed the cure rate from single digit 10s to 20s to 70 to 80%. So enormous increases in cure for CAR T cell therapies. But there's a problem. CAR T cells are only available in the United States, Europe, a small number in China. They're not available in parts of the world that don't have the money or don't have the facilities, because it's an incredibly complicated process to make CAR T cells. This is what you have to do to make a CAR T cell. You take a few billion cells out of somebody's blood. That's done by a specialized machine that takes blood out, removes the white cells, and gives the blood back over and over and over. You take those cells and infect them with a lentivirus that delivers the CAR gene. You then expand those cells for a couple of weeks to make enough cells, so you go from billions to trillions, and then you give those cells back to a patient. That costs about $500,000 per treatment. So it's incredibly effective, cure rates of 70%, but it's very expensive and it's unaffordable. And that's why only certain parts of the world can afford it. We had the idea, could we target all T cells and deliver proteins to them. So we used a different marker on T cells, known as CD5. And CD5 is expressed by all T cells. And you can see here, with an delivery intravenously, 80% of the CD4s and CD8s, 80% of T cells are gene rearranged. They're targeted. So our idea was, could we make CAR T cells in the body instead of having to do weeks of cell culture development? And the idea to do that was to make an LNP that targets T cells, to put the RNA that encodes the CAR molecule in the LNP. So when you deliver it, you now deliver that to T cells that make CAR and put it on the surface and form CAR T cells. We started with a CAR T that attacked fibrosis. We were able to see high levels of CAR T cells in vivo. You can see on the left, it's about 25%. So it effectively delivered. And we used a model system. I'll jump here. So the model is cardiac fibrosis. Just about every cardiac disease, which is the #3 killer in the world, results in some form of fibrosis. Sometimes the fibrosis is pathologic. There is no treatment for cardiac fibrosis. We developed a CAR T that attacks and gets rid of fibrosis. So here we gave a single injection of RNA LNPs, probably cost $10, $20 per therapy instead of $500,000. And we were able to get rid of fibrosis. So you can see here, this is a fibrotic animal, and the red stain is fibrosis. This is a fibrotic animal that was treated with RNA LNPs, and we got rid of the fibrosis, and we returned heart function to normal. So this has huge applications for a variety of cardiac diseases, but it'll also work on fibrosis of the liver, of the lungs, of skin, of a variety of organs. Another thing that we can do is look at bone marrow. And this goes back to sickle cell anemia. So this is the worldwide incidence of sickle cell anemia. And you can see that there's over 5 million cases in Africa, sub-Saharan Africa. But it's present in the rest of the world. India is #2, the Middle East follows behind that. There is no curative treatment. Drugs have been developed that make the disease more tolerable, but you're still stuck living with sickle cell, with pain attacks, often a very debilitating disease. People have developed gene therapy for sickle cell, but similar to CAR T cells, you have to take the cells out of the body, you have to culture them, infect them with a lentivirus, and give them back. That's $1 million per treatment. 300,000 people a year are born with sickle cell, mainly in Africa. You can't afford 300,000 bone marrow biopsies, and 300,000 times $1 million cost. So our idea was to develop an in vivo delivery system. Here we figured out how to target the LNPs to the bone marrow stem cells. The bone marrow stem cells are the cells that make all of the red cells and white cells in our blood. The gene defect is in the red cells. We were able to target stem cells with 85% initial targeting efficiency. And then we did what's called a transplant. So we treated mice, we left them for 6 months, and then we took their bone marrow out and transplanted it into new mice that were irradiated to kill their bone marrow. So here we're measuring the repopulating ability of the bone marrow. And what we saw is that 100% of the red cells, the white cells, the granulocytes were gene edited. So this therapy with a single IV injection fixed 100% of the bone marrow stem cells. We're now looking at moving that into sickle cell gene therapy trials in Africa to simply cure the disease with a single injection of RNA LNPs. It has many other uses. It'll work on probably just about every bone marrow genetic disorder. That includes SCID, bubble boy disease, and a variety of other immune deficiencies, and a variety of anemias and other disorders. It can deliver a therapeutic protein. So somebody who has kidney disease, we give erythropoietin to stimulate red blood cell production. We can now deliver therapeutic proteins to the bone marrow that will work better. Bone marrow transplants are commonly used to treat cancer. They're typically used when everything else has failed. To do it, you have to give people radiation and chemotherapy that kills off their bone marrow. It also kills about 5% of people undergoing the procedure. Now we can use targeted LNPs, deliver a protein that kills the stem cells with no toxicity, making bone marrow transplant very safe to do. So there's just huge numbers of applications. What I'm trying to explain is that modified RNA LNP therapeutics has incredible potential to treat a huge number of diseases. It's really, we haven't thought of everything that can be treated with RNA LNPs yet. And there's now been huge numbers of new scientists coming into the field trying to figure out what they can do, what they can develop, and invent new therapies. So I need to thank all of the people in my lab and all of the labs that we collaborate with who have done this work. And I'll stop there and take questions.
Thank you for that great talk, Dr. Wood. I have a couple questions coming in. Probably say things I gave 50 more. But I'd like to just ask one, two questions on the latent HIV treatment. Don't you need 100% coverage for that to be effective? And how do you get that?
Yeah, so it's a great question, and it's very complicated because it's only a couple % of cells that have HIV in them that can actually make HIV. Most of them are defective. So you're probably talking 1 in a million T cells has latent HIV. We're never going to get an efficiency of 99.99999% to get rid of all of that virus. But our idea is we're combining it with other therapies. So we're delivering HIV-specific CAR Ts. We're delivering broadly neutralizing antibodies. And then combining those three together, we think we'll be able to suppress the virus and get rid of virus, leading to a cure. any one of them alone isn't going to work.
Were you expecting the number of additional shots that people have to get? And do you expect that that will be true with other viral diseases that might be cured with messenger RNA?
Yeah, so what you're addressing is the longevity of the response. And right now we're getting boosters every 6 months, but that's not because the longevity isn't good. It's because the virus keeps changing. New variants appear. If you look at the Omicron variant, the initial vaccine was at best 20% effective against Omicron because Omicron was produced to avoid vaccines. So you can't judge the longevity of the response because the variants keep changing. They're going to keep doing that. For influenza, we make a new vaccine every year because the virus changes and last year's response isn't protective. My guess is we're going to do the same with COVID. We and others are working on universal vaccines that will work against all variants and all versions of the coronavirus. If we can make that, that might have a protection for 5 or 10 or more years. We don't know yet. For viruses that don't mutate, that don't form variants, like the herpes family, it could be the vaccine protects you for 20 years, longer or shorter. We just don't know yet.
I have a question from a student.
Okay, so this is a bit of a different question. So how do you balance your passion for like research and trying to find solutions to these diseases with like the problem of public health access and problems with equity?
Yes, so one of the good things about getting old is you don't need much sleep.
Oh.
So sorry for the older folks in the group, but I don't need a lot of sleep, so it gives me more time to work. And you know, when working with Thailand, China, Vietnam, Southeast Asia, they're 11 or 12 hours behind us. So, you know, I talk to them at 4 a.m, and we design experiments and we design clinical trials, and you know, I just find time to do everything.
Okay, and then my other question was, since you've worked in the US and Africa and Thailand, what have you learned about sort of like working around the same field but in different countries?
So my dream, and I've had a lab in Thailand for 30, 35 years. I've had a lab in Botswana for 25 years. So I have a lot of experience working in these countries. The people there have as good a brain as anybody here. What they lack is the education and the facilities. So one thing we've worked on is giving the facilities to do the research for these countries. And it involves bringing equipment on our backs sometimes. But once they've got the facilities, they're as good, if not better, at doing research than we are. And their educational systems are excellent. So there really isn't much of a difference. The biggest problem is just access to the best equipment.
So I know you were talking about like CAR T cell therapy, about how like it could be used against cancer. Can you like describe that again? Because I didn't really get most of it.
Yeah, so the CAR Ts rely on our immune system. And our immune system has a type of T cell known as a CD8 killer. And these cells are very effective at killing virus-infected cells and cancer cells. So what people did, namely at St. Jude and then followed up with Carl June, is they changed the killer T cell. And they added a better T cell receptor that recognizes the antigen. So now instead of recognizing a short peptide that CD8s usually recognize, they recognize a tumor antigen, an antigen that's expressed by all the tumor cells. So now what happens is you make that CAR T cell, it kills every tumor cell that has that antigen and results in cure in around 70% of people. So you're reshaping the immune system to recognize specific tumor cells instead of to recognize short peptides that are expressed everywhere. Does that help?
Hi, I have sort of two questions. One is, what viral protein or surface structure is the target for the pan-coronavirus?
Yes, so as you're pointing out, that it's complicated. We work with somebody at Los Alamos who has supercomputers who analyze sequences. And what she did is she looked at every coronavirus sequence ever identified. And 2 years ago when we started, she found about 500,000. And they ranged, some of them were SARS, some of them were MERS, many of them were a variety of bat coronaviruses. So viruses in bats that could infect people but haven't yet. And then she lined them all up and looked for conserved regions. So regions that were identical in all of the different coronaviruses. And then we use those to make a vaccine because if the site is conserved, it means the virus can't change it. And it means all the different viruses we want to protect against have that sequence.
Thank you. The other question I had was about DNA vaccines. So I know that there's like a West Nile virus for horses that's used as a DNA vaccine, but we don't have any human ones. Do you think that the development of the mRNA vaccines will encourage DNA vaccines, or will everything sort of shift to?
So I didn't put this slide in, but the greatest fear of every vaccinologist is that mice lie. So that means everything you try in mice works. Every vaccine works. Monkeys exaggerate, which means the vaccines might work in monkeys, but they rarely work in humans. And that's what DNA suffered. So when DNA was developed, it worked great in mice. It didn't work well in monkeys, and it didn't work at all in humans. And it was dropped for a long time. And then people like David Weiner figured out if you add electroporation, it would make the vaccine work better. That they've got an HPV that leads to warts, cervical warts, that's in clinical trials and looks great. They tried to make a COVID-19 vaccine, and they did a phase 1 clinical trial. And the plan was people would get 2 doses, and they would see what happens. The problem was nobody came back for the second dose because it required electroporation, of getting a shock. And people didn't like getting the shock and wouldn't come back for the second dose. So I think DNA vaccines are going to have a limited use. You know, people aren't going to get an influenza vaccine when they get shocked.
Drew, fantastic talk, really wonderful work. I'm curious about Thailand, the Thailand results, and what did you and your team make of their greater efficacy?
So we started making COVID-19 vaccines around January 20th of 2020, when the sequence was first released. And at that time, everybody guessed what to use, how to make the vaccine. Moderna and Pfizer both guessed, and within 2 months, they were immunizing people. We started the Thai vaccine a little bit later, so we were already doing mouse studies, and it let us pick a better version of RNA, and that RNA worked better and gave a better response.
Drew, awesome talk. The biggest vaccine producer in the world, I believe, is the Serum Institute in Pune, India. Have they started using mRNA-based vectors?
So we've talked to them, and we've been helping them make RNA vaccines. The big problem that's a concern for us also is that they made adenoviral vaccines, but none of it was available to people in India. And for us, that's a big problem, because you have a huge vaccine manufacturer that isn't supplying vaccine to their own population. It makes us question, do we want to work with groups like that?
The economics.
Yeah.
Just one more.
And with regards to the vaccine technology for autoimmune disorders, are you looking at Crohn's disease or other things intestinal?
So the problem there is you have to identify a specific antigen that's associated with autoimmune disease. So for type 1 diabetes, we know the antigen that's attacked. For Crohn's disease, there are many different antigens. And Crohn's disease is actually an immune deficiency, even though it's an inflammatory disease. So we don't think vaccines will work well for Crohn's disease. But we're looking at others, things like rheumatoid arthritis, lupus, where we know the antigens and we can make the vaccines.
Are there any other questions? Yes.
You know, one of the problems that the anti-vaxxers have is that children are being inundated with 30 shots or whatever it is. Do you think that this technology will work by combining, you know, multiple RNAs so that you have 5 shots instead of 30, because each one has 6 different, you know?
Yeah, no, it's a great question. We have made RNA vaccines that have 20 different RNAs in it, and they work well. I always get yelled at by pharmaceutical people when I say that someday your child might get 1 shot at 6 months, at a year, at 2 years, and be done. And the 20 RNAs will give the main diseases that they're vaccinated with. I don't know if that will ever happen. Pharmaceutical companies don't like to give up on things that work, but it's possible.
I know students have to leave for the class and sports people have to leave for sports. Because of your research work, Drew, the future is full of hope, and people can look for all the future medicine is going to be much more rapid. And your name, Drew Weissman, and RNA and vaccine and PCR have become a household name. And you are to be commended for all that you have done for your lifetime research. We are so happy that you're here. It is truly a humbling feeling for me to meet you in person. And I'm so grateful for coming to Chestnut Hill College. You have made my day. You have made my day at Chestnut Hill. On behalf of our president, Dr. Latimer, and the college communication, we are so grateful for your presence. Our president, Dr. Latimer, will like to offer you some token of appreciation. And it's very small, but we are going to give you as a token for your coming here to Chestnut Hill College. Thank you all very much. Please give a round of applause. Thank you so very much. He will be around. Please stick.